And we're going to answer this first question. Which type of reactions are always thermodynamically favored? Those spontaneous ones, and that's a certain type, Brian. Which one would that be? Yeah. Doesn't it say right there? Yeah, what types of reactions are always exothermic and increase in entropy? Types of reactions. Not decomposition. Usually those, I think, are mostly non-spontaneous. But
explosion.
Thank you. Combustion. Well, he needs to speak up. He's too quiet. We can't hear him. He's talking like this. Combustion. Now, what you should know, obviously, these give off so much heat. They're hugely, and they have a high exothermic release. Delta H is very, very high here. But you should also, especially for the looking just at the complete combustion ones, you have a carbon compound, you have some oxygens, but they create lots of carbon dioxide and water molecule and gaseous. Sometimes the carbon compound starts out as a liquid. Okay? So it definitely increases in entropy as well, but the huge, huge exothermic release and combustion reactions are always going to be spontaneous. Now, going back and revisiting some of the concepts from the last set of notes, looking at the melting. Okay? Using Gibbs free energy equation, explain why it is only thermodynamically favored at high temperatures. So, have a little discussion. Think of using the equation, try to think it through. We're really going to hammer down the conceptual knowledge here, as well as being able to plug and chug in the equations. Okay? Here, just to recap a little bit too about the melting, freezing, boiling, condensing, those wonderful phase changes, because really what we're dealing with here is we're not actually changing substances. We're not doing a chemical reaction. They are the same substance, but they have to break either intermolecular forces. In the case of the gallium here, where it's melting in the palm of the hand because it does melt at, almost room temperature, that would be metallic bonds because those are the metal is holding itself together there. And we haven't really gone into metallic bonds, and you probably haven't ever heard of them, but they have to break a little bit in order for it to liquefy. And over there in the water, the stuff holding the ice together would be what type of intermolecular force? Hydrogen bonds. We know that's HO or HF or HN. H-bond, remember those hydrogen bonds. Holding it together, so we have to break some of those forces to get it to spread out and become a liquid. So that's why melting, going from solid to liquid, and boiling liquid to gas involve being endothermic processes because you're breaking bonds, breaking forces. Whereas the other way, liquid or gas to liquid to solid going the other direction, bonds and forces are forming, so those would be energy releasing, and those all would be exo. So we got to remember those directions for our phase changes. Even though they're not reactions, you still need to know them. Now, going back to the Gibbs free energy as to why when you melt something or even boil it, your entropy is going to do what? Entropy is going to increase because you're going to get more random. So entropy is going to increase. I can write on the board. Okay, and if we're looking specifically at our equation now, the delta G equation, delta G equals delta H minus T delta S. Okay, this component of the equation at high temperatures is pretty much going to override the delta H there, and this therefore would be entropy driven, like they said in the video the other day. But it only works at high temperatures because if the temperature is too low, then the enthalpy would be higher, and you get a positive delta G rather than a negative delta G. Okay? So you can be asked questions like that as well as the plugging into the equation type and then signifying it. So you definitely need to understand the conceptual behind. Okay? Okay, so now you're going to be looking at the exercise here, practicing some of the concepts with the phase changing. And let's review a few things too. Enthalpy of fusion, how is that noted when you would see it on a paper? How does the delta H look? FUS, you'd see it like that. That is for freezing and for melting. It would be positive for melting because that's endothermic, but the number would be negative for freezing if you were going the other direction. And how do we know the other one, the one where you boil or condense? Delta H, yes, delta H VAP is going to be for boiling and for condensing. So if you see that, you know it's going to be another one of these phase change type problems. Boiling and condensing. So, for the first part here, I'm sure you can figure out what you're going to do, and then we'll talk about getting the melting point in a second. So go ahead and calculate real quick.
Yeah, I
know. I asked you.
Okay, so our answer ends up being negative 0.13 kilojoules per mole. So will the solid ammonia spontaneously melt? That would be a big yes. It's going to melt. Now, how can we figure out part B? What is the approximate melting point of ammonia? What is delta G while it's melting? What is delta G value when we're melting?
0.
It's 0, right? So, can't we substitute in 0 for our delta G and calculate the temperature? Right? Yes? Oh my God.
No, that is right. That's wrong. It's wrong.
It's going to be 0.
Oh my God, it's right. It's wrong.
It would, yes, this would.
Oh.
Thank
Oh
you.
my God, it's actually so nitpicky.
There you go, correct number of sig figs. Now, looking down here though, if you rearrange here, okay, doesn't it become T equals the delta H value divided by the delta S value? Did you rearrange and see that? Okay, so we could figure out our T now, and what is T? 196K. And here you would use 3 sig figs since you're dividing. Yes. Not subtracting, but good point on the subtraction. So, when things are melting and at the melting point or freezing point, we know it's in equilibrium because it's like that plateau on the heating curve too. Okay? So that means you really can have a new derived formula from this, where the temperature is always going to be the delta H over the delta S when you're freezing, melting, boiling, because you're in that equilibrium phase, delta G is going to be 0. So this is a new, lovely derived equation, but that only works when we're at equilibrium, of course, during the phase change. Moving on to the next one. This is kind of the stuff that you're going to see in your problem set, is the time-consuming stuff, where you have to go look up the information in the appendix, although here it's given to you in the table. But you need to calculate delta H, delta S, and delta G. So when you're doing the delta H and S, what equations are you going to use there?
Delta H.
The delta H, what? Products minus reactants. Good. The sum of the moles of the product times, adding those moles and the products up minus the moles summed up with the reactants. And both delta H, delta S, and delta G, products minus reactants, are all on the formula sheet. Okay. The other one, the delta G equals delta H minus T times delta S, is also on the formula sheet. Just so you know, you can look at, they're under the thermo section. Okay? So that's what I'd like you to do in the next couple of minutes. Go ahead and calculate all three.
I'm sorry, I didn't sign any waiver forms until after these interest frequency.
I'm like,
Oh.
Okay, so here we end up with negative 142 kilojoules per mole. And this ends up being negative, which is the key thing here. So we would say this one is thermodynamically favored. Thermodynamically favored. And you should see on free response questions now, like so, they'll might have a piece from equilibrium. They might have you do delta H, then delta S, and then combine them in a delta G. So they'll start to mix up a lot of these concepts now, as you'll see, because I'm going to give you some free response next week to practice with, that a lot of these things are going to start to merge. Just like in the next equation that we're looking at here. Because
Yeah, why is it even though
all right, looking here, if you're given the delta G's, as you see, you can do the same kind of thing that you would do for Hess's law. Works for delta G as it does for delta H, I suppose, because they're state functions. So go ahead. What would we want to do here in order to figure out our delta G for the overall reaction of diamond solid changing into carbon graphite? Okay. Okay, so what do we have to do here? Which one do we need to alter? And how do we alter it? Flip the second one. So we're going to change this one around. CO2 going to give us C graphite plus O2. Therefore, we can cancel. Okay, that means this guy's sign over here now becomes plus 394 kilojoules. So we get a negative 3 kilojoules for the overall reaction there. So what does that mean? It is thermodynamically favored. What also does that mean about the reverse? And does that make sense? C graphite changing into C diamond, because diamonds are made of carbon, you know that, right? What do you know about diamonds being formed? What? Lots of pressure and heat. You need energy for it to occur, so it's not spontaneous and it is not thermodynamically favored. So the reverse would be in that category. Now, the non-standard conditions. So far, we've been working with everything at standard conditions. What are standard conditions again? 298 K, which is 25 degrees Celsius. 1 atm, and concentrations are 1 molar. Okay. Now, at non-standard conditions, the non-standard delta G over here equals the standard delta G plus R times T. This time you make sure you use the ideal gas constant where it's 8.314 because it's the one with the joules in it, and this is the one that meshes with all of these equations. This one's on your formula sheet, and some people inadvertently use the wrong one on the kinetics test. But this is the R value that you want to use. Temperatures in K. Now to find Q, we've got to recall some stuff from Unit 3, like equilibrium expressions and so forth. Okay? And we're going to look at an example in just a minute. You can use pressures if it's all gases. Remember, you can use it for the gases problems because you can do KPs from there. And then if it's not at equilibrium, you can insert the Q instead to find out which way it should shift to go to equilibrium. And then, of course, Kc was with the concentrations there. Okay? So you can use this equation in order to find information about delta G when it's at a non-standard condition. So, next exercise is on using that equation. You might have to do a couple steps there too, because I believe they give you delta H and delta S, not the actual standard delta G, so you have to find that first. So, go ahead, take some time to do that. Okay, so calculating. Looking at our delta G standard. Okay, so you get that first, solving from your delta H and delta S. Make sure that you look at your units here. Make sure that you do that correctly. Now the second part is doing the Q. Remember, you're following the KQ expression here, so it's always going to be like K is normally the products of the reactants raised to their powers of the coefficient in the reaction. So on top would go the 2.0 raised to the second power because it has a 2 in front of it. On the bottom, we would have 0.75 and then 0.75 would be raised to the third, right? And then the nitrogen was 0.5. And Q ends up being 19. Then you can plug it into the non-standard equations. And here you have to make sure that you're using joules. I put it into joules here because it has to coincide with the R. So for delta G, and it ended up being positive here. So you can see that it would be not thermodynamically favored. Did it come out negative and I didn't write that down? Oh, then it would be thermodynamically favored. Came out negative, sorry. I apparently didn't write my sign down. Now, this is at non-standard conditions. However, we use the Q we put the Q in there, but now we're going to relate delta G directly to equilibrium. Okay, we already know delta G is what at equilibrium? 0. So we can manipulate this equation and substitute. Okay, so if delta G is 0 here, you can push this over to the other side and flip the signs, and you end up with an equilibrium relationship for delta G at standard conditions. In this case, the K is representing the equilibrium constant. And as you can see, it's this point on the graph here where the delta G equals 0 that this holds true. Occurs at the lowest value of free energy available to the reaction system. Okay? Okay, so how does this relate to K directly? If you know the K, you know the delta G. So, delta G is 0, K equals 1. K equals 1, we're at equilibrium. We're relating, of course, K products over reactants. We have the same amount. Okay. Delta G is less than 0. K is greater than 1. You're going to completion. Products are favored. Okay, so products would be favored. And if delta G is greater than 1, that means K is less than 1, so the reactants are bigger and favored. So if you know K, you can figure out delta G. If you know delta G, you can figure out K. If the system's at equilibrium. So here, yes, relating this to the negative delta G, the positive delta G. Okay, so let's look here. And what I'd like you to do first is think about Le Chatelier's principle and indicate which direction it's going to shift first before you try to surmise what's going on with delta G. So make sure you indicate which way it's shifting first before you're trying to figure out the delta G value. So yes, a little bit of review from Unit 3. When CO is added, which way does it shift? CO added shifts to the right. H2 is removed. It's going to shift. It's going to shift left towards the reactants. Pressure's increased. Pressure's increased. It's going to the right. Good. Size the least number of moles. And temperature is increased when delta H is negative 85. So that means heat goes here on as a product because it's exothermic. So if we increase, which way? It's going to go left. Good. And if we add some more methanol in there. Adding some more methanol in there.
No change.
No change. Good. It's a liquid, remember, not affecting equilibrium. Now take a moment to think about your delta G's. If you're shifting to the right, who's increasing? K is increasing. If K is increasing, delta G should be decreasing. Yes, becoming more negative. Okay, delta G is becoming more negative and decreasing. So I guess we should negative there, but you should say delta G is going to get lower. You're making more products, delta G goes down. If you're making more reactants, delta G should get bigger, and getting bigger, becoming more positive. Okay? So therefore, 3 obviously should be decreasing again. Delta G will decrease. And 4, delta G will increase. Now, how about the last one here? This is the delta G doesn't change because you're at equilibrium. Good.
So is that delta G?
So the delta, if you're not changing the position, the delta G isn't necessarily at 0 there, but is the delta G going to change? No, because it's nothing affected the system at that point. Okay. Exercise 14. So this one is more of, let's use the equation now. Okay? So let's use the equation. Okay, so you are right. The delta G would be 0 because it's at equilibrium. But we're not shifting it at all, so nothing changes.
So it doesn't change is the same thing as equal 0.
Well, it's going to be equal at 0 at that point because we're at equilibrium. But we're not changing it all because that particular case in letter or in number 5, nothing's shifting.
Right, because it's a liquid.
Because it's a liquid. Exactly. Okay, so let's plug and check.
Yeah.
Now K is small here. So K is small here. Therefore, which direction is the reaction spontaneous? The reverse is spontaneous, so this way, reverse. And which side would be favored then if it the reactants?
No, I was talking about the direction. I literally said this.
The reactants would be favored at equilibrium, and the reverse would be favored here at this very large temperature. Okay, now you're just continuing on with the variations in the practice problems, a couple more exercises. And number 17, exercise 17, is more of like a free response too, where it's applying a lot of these concepts to some solutions now. And you'll see how you can use them for these varying different equilibrium situations. And so move on to number 15. Yes, in the first part here, you are wanting to make sure that you... Oh. Did we already do exercise 14? No, I didn't finish. Did finish exercise 14. Okay. For exercise 15. What you should see here, and you can kind of help yourself skip a step if you want to, is if delta G equals delta H minus T delta S, delta G also equals negative RT ln K. What can you do with them? You can set them against each other and kind of merge it together. Okay, since they both equal delta G, you can have all of the variables in there together at once. Okay? So, over here then, this would be, if I'm following this format, having changed this to joules, joules per mole, that's the delta H minus T, 298 times, this is the joules per mole. Okay. This equals our negative 8.4 8 times L. So if you break this down, you get ln(k) is 2.18, and yes, you would need to do the k equals, I can write equals today, e to the, so k should have come out to be 8.85. 2 sig digs?
Yeah.
No,
Whoa.
He's right. It's because when you subtract over here, when you subtract it's gonna be calculated like.
but you subtract here, this ends up being 10, so that's 4 significant figures.
We use kilojoules.
Oh, well, there you go. We got it. So,
It does.
anyhow. Uh-huh.